Hello everyone. So in this video we are going to review chain rule. Now why is that? Trust me, it's worth of time. If we understand chain rule perfectly, we can understand integration by substitution very easily and we can do it very easily. Okay? Alright, so it's worth of time. So let's review chain rule. Now why do we use chain rule? Look at function e to the x and another function x. Now this is an exponential function, this is just a x, right? X square, let's say it x square. Now how about the third function e to the x square? This we called a composition function. Now that's a little bit of uncomfortable word. Now here's the way to explain it comfortably. E to the x square is a function inside another function. Now the outer function is an exponential function. Do you see it? It's e. Now the inside function, inside e you have x square, another function, right? Now instead of the variable x in exponential function, you have x square, another function x square. Okay, so this is a composition function, or the best way to explain it is an inside function inside an outer function. Okay, so now when we have something like that, we use chain rule to differentiate a function like a composition function or a function that is inside another function. Now how do we do not integration, how do we do differentiation, how do we do chain rule? The chain rule says, okay, it's like an orange, peeling an orange. When you are given an orange, first you peel outside, right? So look at the outer function. The outer function is the exponential function. So what do you get if you differentiate an exponential function? If you differentiate e to the x, what do you get? You get e to the x. So if you differentiate e to the x square, think that you get e to the x square. Now what you do is you are done with the outer function. Now you go to the inside function. The inside function is, the inside part is just x square here, right? Differentiate x square separately. So derivative of x square is 2 to the x. So multiply the previous function that you got, the derivative of outer function, by the derivative of inside function. This is the derivative of e to the x square. So that is how we use chain rule. Differentiate the outer function, then go to the inside function, differentiate and multiply 2, both of them. So let's do some exercise. Okay, so be with me until the end of the video because it's going to be very interesting. There are a couple of things that are very important to us. Now let's differentiate sine x cube. What do we get? First look at the outer function. The big function is sine, right? Derivative of sine is cosine. Now cosine x cube. We don't change that x cube. Now let's touch x cube. The inside part is x cube. The derivative of x cube is 3x square. So let's write as 3x square. So here I differentiate. Let's go to the third one. I'm not going to do the second one because if I'm going to do the second one, I have to do recall some differentiation rule basics. So I'm not going to do that. I will leave it for you. Derivative of cosine is negative sine. Negative sine 3x. So that's the derivative of outer function. Now go to the inside part. Inside part is 3x. Derivative of 3x is 3. Right? So it's negative 3 here. So that's the derivative. E to the negative 2x. Derivative of exponential function. Outer part is e to the negative 2x. And the inside function is negative 2x. Derivative of negative 2x is negative 2. So let's multiply by negative 2. So these are the derivatives of the function that are given on the left. Okay, now I want you to notice something very important, or understand something very important. Okay, here's the phrase I'm gonna say. When we use chain rule, when we differentiate that outer function, we pretend that our inside function as a one variable. Now what do I mean by that? This is very important. Okay, this is super important. When I differentiated e to the x square, okay, first I differentiated that exponential function, but I treat him like e to the capital X, for example. Okay, I pretend that that inside function is not there, or I pretend that inside function x square is like capital X, and wrote it as e to the x, because derivative of e to the capital X is e to the x, and then later differentiate that capital X, then later differentiate that x square and multiply by it, right? Okay, so that's super important. Look at here, same thing happens here, right? I initially thought this as sine capital X. Derivative of sine capital X is cosine capital X, right? That capital X is x cube. Then later I differentiate that inside function. Now pause the video and think about it. Is this the case for all these functions? Think about it, okay? Try to digest it. Alright, so now on that note, let's look at these solutions. So these are the solutions. So say if you differentiate sine x cube, we already did this, right? Okay, now if you look at this very carefully, I have two colors in the result. So if you differentiate sine x cube using chain rule, I get 3x squared times sine x cube. Now look at those parts that I have highlighted from red color. What are those parts? How can we give a general name for those red color function parts? They are the inside functions, right? X cube is the inside part of sine, right? The big function. X square plus 1 is the inside part of that square root. Cos 3x is the inside function of cosine, the big function cosine. Negative 2x is the inside function of the exponential function, right? So the red color parts are the inside functions. Now look at the green color parts. What is the relationship that these green color parts have with the red color parts? Think about it. They are the derivatives of the inside function, right? Derivative of x cube is 3x square. Derivative of x square plus 1 is 2x. Derivative of 3x is 3. Okay? Derivative of negative 2x is negative 2. Do you see that? Now here's the important thing. So when you apply the chain rule, when you use chain rule to differentiate, in the result you have inside function, and outside somewhere you can find its own derivative outside the function, right? So derivative of x square, it's outside, you can see it's 2x. Derivative of 3x, it's 3, it is outside. Derivative of negative 2x, negative 2, it is in outside of the outer function. That's a one characteristic that you can see after you apply the chain rule, which is super important to integration by substitution. Okay, what is it again? I'm gonna say it again. You can see the inside function and its derivative outside that big function. Both of them are in the same place. Now here's the cool part. Now why did we spend time 8 minutes for this? Because we did differentiation from here to here. We used chain rule. Now if you want to reverse the process, think about this. If you want to reverse the process, you have to integrate. Here we are going to use integration by substitution. Now how do I know whether I have to use integration by substitution or not? If I can see my function have an inside part, inside function, and not only that, its derivative also there are somewhere else outside that main function. Okay, then that's a hint to say that we have to use integration by substitution. For example, look at this. This is the question that you get. Let's say this is the question that you have. Now they ask you to integrate this. If you look at this, okay, I can see there's an inside function x cube, and its derivative is also outside 3x square. So now you know I have to use integration by substitution. Now you know something else. What is that? This function is obtained through chain rule by differentiating some kind of a function through chain rule. You know that also. Okay, so the counterpart for chain rule, the undo button for chain rule, is integration by substitution. To identify that, we use the fact that inside function and its derivative exist together in the same function. Okay, so that's a hint towards identifying integration by substitution problem. Okay, now that's in very simple sense. Okay, that fact can be used to do our simple homeworks, medium level homeworks. But when we go to the harder level problems, you might not able to see that very clearly right away, but we are going to learn that also. But that fact is enough to get a start. So to extend on this discussion and really go to the integration by substitution, you can click the video that appears on the video right now, in this video right now, and then I will see you in this video. Until then, take care. Bye bye.